So today we're going to talk about how energy is stored in rocks and how those rocks will release that energy when they fracture, producing an earthquake. And we know that earthquakes come from well-defined zones, areas where there's a transform, divergent, or convergent plate boundary. The earthquake's epicenter is often found by analyzing where the waves come from using 3 seismic stations. That's called triangulation. We'll talk about that. We'll talk about the intensity and how we measure that intensity using 2 different measurement scales. One is a qualitative assessment, which shows you the amount of damage that's done by the earthquake, and then we also use the Richter magnitude or the moment magnitude scale, which will tell you how much energy was released. We'll talk about the hazards associated with earthquakes, ground shaking, fire, tsunami, and ground failure. We'll also talk about how the internal heat drives this process. And it's actually pretty stable even though we do have earthquakes. The amount of energy released in an earthquake is really small compared to the amount of energy that we have on planet Earth. So here we show a picture probably from Turkey or somewhere in the Middle East where there was an earthquake, and I'm sure a lot of people died because these buildings collapsed. They look like apartment buildings, and that's a result often of their building codes. But we know that earthquakes are very destructive. They can cause many deaths and injuries, and they do every year. In the United States, we tend to have building codes that prevent a lot of building failure, but the most important thing related to surviving an earthquake is know what to do when one hits. So when an earthquake hits, you should know that you should get under some sturdy structure so stuff doesn't fall on you. That's primarily how people die, is stuff falls on you. And then so during an earthquake, you should get in a door jamb or in a stairwell or somewhere where you are under your desk, wherever there's going to be some protection. You're not wearing a hard hat per se. And then before an earthquake, you should have an earthquake kit, which has water, basic batteries, lights, things that you can, basic food source, so that you can get through anything where if you get trapped or you happen to have need to help someone else. But in Michigan, we don't worry about this so much because earthquakes are, well, they're fairly rare. Did have one last year that we felt, but it was actually down in Kentucky, I think, where they actually hit, or maybe it was Pennsylvania. But anyway, and after an earthquake, you should know that you should get out of the building, do all the stuff that you would do if there was a fire, because when things become unstable, and houses often catch on fire when there's an earthquake, you should get out of the building. So, earthquakes, we know, are the sudden release of energy that's pent up in the rocks, and it most often occurs along a fault when that fault fails. And this produces a shaking or trembling of the ground that results from those waves of energy moving out from the source of that rock fracture or fault, or the failure of the rock. And most of these occur on plate boundaries, and that's why we have so many earthquakes around the Pacific Rim, which is the Ring of Fire, because of all that subduction and plate interaction that's occurring right there. So if you remember, when we were talking about how rocks build up energy and they have a certain elasticity related to them, well, they rebound after they reach a certain point at which they can no longer elastically change, which means they rupture, and they've reached the elastic limit, and they return because of the elasticity of the rock back to their original form, which then releases this energy as a wave as the rocks deform and bend and then return back to what they were like before the deformation. And the pressure that results from this is quite high, and it results in a huge release of energy because rocks are very stiff, and so when they return to their form, they do it very rapidly. And when they rebound, they release all that energy. And when they do release that energy, we record it using a seismogram. So a seismogram is actually the device that we record a seismograph. The seismograph is actually the reading. It's the big drum, as you can see here in this picture, and they have a graphic down here. Or the book has a graphic that you can see. And so what happens is, as earthquakes, it'll be some background information. This will be moving, and then if you get an earthquake, it'll get really big. It'll sort of show you how it'll jump, and then there'll be another wave usually coming next. And you can read the amount of energy at that site, because as it shakes, the bedrock shakes, it transfers this energy to the actual arm, the pendulum, which is suspended on a cable here. basically stays stationary. Well, eventually it will swing if the earthquake lasted long enough, but it's not going to absorb much of that energy. But the drum, the seismograph that you're recording it, records how the bedrock is moving. So what happens? Well, we have these faults as the plates come in contact and they rupture or they build up pressure and then they slide across each other. They build up contact points that stick. And then when those contact points reach a point where the elastic limit of the rock, like we said, they slip, and that's what you're seeing. And you'll actually see the slippage on the surface of the planet. In this case, if I were to ask you what kind of fault this is, you should understand that this is a reverse fault because the hanging wall, which is this side, is moving up with respect to the footwall, which is this side. And so you actually have a reverse fault here. And when this reverse fault fails, it sends these waves through the rock. And we remember we had this earthquake in Sumatra that had the huge waves that came out and hit Sri Lanka and India and a few other places, and a lot of people died. It was 250,000 people died all in like a very short time period, within 12 hours, as this wave propagated across the ocean, the Indian Ocean. And when we look at how earthquakes, the structure of earthquakes, we have a focus, which is where the rock ruptures, and we have the epicenter, which is right above where that focus is. And then we have the wave ray, or the energy that's moving. They have a wave front, and then the fault itself, which we just talked about. But in effect, we can record the amount of energy coming off on the seismograms, and we can actually locate where these occur based upon having 3 seismograms set up. What's interesting about this is the damaging earthquakes are when the focus is near the surface rather than really deep. And the reason for that is the energy travels very rapidly and is transferred along the surface much more effectively than if it's really deep, because the rocks that are really deep are going to absorb some of that energy before it reaches the surface. And here we have the seismology related to the big earthquakes like on the Tonga Islands, New Zealand, and why we have, well, we know about the island chains. When you have 2 oceanic plates coming together and one subducts under the other, you end up melting some of that magma because of the boot effect. As the pressures change, temperature remains the same, but the pressure drops, which means you liquefy that rock, and plus there's water from the ocean that's in the rock as well. But the relationship exists between the type of boundary and how deep the focal effects of these earthquakes are. And the foci this is called the Benioff zone. This zone right here, where we see the earthquakes occurring along the plate that's subducting, that's called the Benioff zone. And that's we can mark the location of the earthquakes on this, and by doing that we can actually identify where the subduction, how far the subducting plate, is going down, and where those earthquakes occur. And that often they'll occur at 100 miles below the surface, or 25 miles. The ones that are more near the surface can be related to the movement of magma, but they can also be related to the slippage of the mantle and the oceanic plate. And as I mentioned before, we have this area where we can record, or where we record all of the earthquakes, and the one where we record most of the earthquakes is called the Ring of Fire. And if you get on the USGS website and look up earthquakes, it'll take you to a earthquake recording web page. It'll show you where all the earthquakes have happened, and you can go back, you can set the time frame so you can see how many earthquakes happened over this certain amount of time, and they'll show you where they happened on the earth. But in this case, you'll see all of the deep focus earthquakes are happening along the Ring of Fire, which are the red ones. We don't have many deep focus earthquakes up here in North America, which is good and bad depending on how you look at it. But we have about 900,000 earthquakes a year, and 31,000 of those are strong enough to be felt. About 80% of all earthquakes are within the Circum-Pacific Belt, and 15% of those are within the Mediterranean Asiatic Belt. So that would be over here. Wait, where's the Mediterranean? Over here in the Mediterranean, and then down through here in this area. And what you realize is that's 95% of all earthquakes happen along these subducting plates or where you have contacts between different plates. And the rest of the earthquakes, the 5%, generally occur along the divergent plate boundaries or the spreading ridges within the plate interiors. And here's what happens when you have a seismic wave moving through material. And the way you look at this is they have boxes, and right here, the boxes that are squished together, that's actually bringing 2 points in space closer together because you're compressing the rock. So it actually is getting compressed, and that material moves through, the wave moves through by compressing, and then that's the elasticity of the rock, the compression, and then it gets released as the elasticity of the rock rebounds to what it was like before, and that wave propagates. And this is called a primary wave. These are compressionary waves. You got to remember that. This is a compression wave. And then you have the sort of the shaking waves or the secondary wave. This is the up and down movement as this wave propagates through. So these would be the kind of waves we normally see in water, even though you do get the similar compressionary waves, but we don't normally think about it like that. We normally look at the waves that are sort of these up and down movement in the water. And these tend to move in a circular pattern. If you were to sit in a fixed space, meaning find one of these spots where these triangles, or sorry, these squares or cubes cross, you'll see that this moves in a circle as these waves move past it. And remember that. So the primary waves are compressionary waves, the secondary waves are the up and down movement of the waves. And what happened here is if you're on the surface and you're right under the focus, you get both compressionary waves and moving back and forth, which is the worst place to be because your house falls apart. So the seismic waves that cause the most damage that people feel are these two kinds of waves, the seismic waves of the P wave and the S wave. That's primary and secondary. And then we have some other waves that we'll talk about, which are the Rayleigh waves, which are the circular motion of these waves as they move through, the undulation of the waves, and these will open up a little bit of space, but they work in conjunction with the secondary waves. That rolling motion, these are surface waves, right? So the movement of back and forth as these waves propagate through the ground, and I said they move in a circular fashion. What you see on the surface are the circular waves, which we normally think of like the waves in the ocean. And then, of course, we have the love waves, which are these blocks that are moving back and forth, and this is a shearing effect, right? So what you see in the road here is you have the Rayleigh waves, which are moving in a circular fashion, and then the love wave, which shakes it back and forth. And these are, you can see this happening actually if you are in an area where you have a lot of earthquakes. You look out and the Rayleigh waves will cause the telephone poles to rock back and forth. They're not really that dramatic and they don't really cause a lot of damage, but they, if you get some amplification effects because they work in unison, you can have some real issues. But in most cases, it's the primary and secondary waves that we worry about the most. So how do we figure out where these earthquakes happen? Well, like I said, we use a process of triangulation with 3 seismograms that gives us seismographs, and they look like this. You have background noise, and the first primary wave hits. That's the fastest moving wave, the compressionary wave, and it shakes it, and there's a pause. And then you get the secondary waves, which is that undulating kind of wave, and then you have the long waves or the surface waves as well, which are then shaking it over. These are the surface waves over here. And you can look at when the first wave arrives and then the secondary wave arrives, so the primary and the secondary, and there's a time interval between there. And because we know how fast these waves move through rock, we can then go back on our logarithmic scale and look to see how far apart they are and where they happen. So here we have the distance, time, travel distance. So this one arrived at like, I don't know, minute 12 it looks like, and this one arrived at 23. And since we know how they travel through the rock, we can say here's the interval between them. We match them up, and we know the distance in focus is, in this case, about 8,500 kilometers away from this one station. So we can plot the time distance on the graph, and we look at the difference between the arrival times of the P and the S waves, and this is used to determine the distance from the seismograph of the focus. But as we do that, because you don't really know if, let's say you have one, it's a circular ring, or ring, that's what a circular ring is, a circular ring around whatever seismograph that you have. So the first thing that I want you guys to look at when you look at this is, let's say you're in probably LA or San Diego. I'm sorry, San Francisco, and this is that what it says? This is Berkeley. Yeah, it's not, it's Berkeley, not San Francisco, but it's close. And they receive the primary and secondary waves, and they say, oh, we're out this far. So if you just have one seismograph, you know you're at a distance, but you don't know where in this 360-degree distance it was. Then you get the reading as well, which is a little bit later at the Denver one. It's a little bit further. And you know that if you were to look at this, you could cross these over and say, we know that there are two spots because we have two seismographs showing distance relationships here, but we still don't know the specific one. And then there's one in New York, which means that the only place that this could occur is in that one spot. X marks the spot, because all three cross at that point. If you notice here, they are close, but they don't cross. They don't cross at one point. And this is pretty good. They can do a lot of investigative evaluation of earthquakes, or if the people are setting off nuclear weapons. That's how they determine if someone sets off a nuclear bomb, because it sets a different kind of wave through the Earth. But the simple movement of the Earth doesn't give us the destructive effects of earthquakes. There are a variety of things that go into this. It's the movement of the fault itself, like the direction if it's lateral or up and down. It's also the relationship between the type of soil or bedrock or whatever is underneath. And we can look at, this is for a San Francisco earthquake. You look at the bay mud, the alluvium that's less than, here's, it's greater than 30 meters thick, here's less than 30 meters thick, and then you got the bedrock. And if you notice, whenever there's bedrock, the amount of shaking that occurred during this earthquake was much less than the other areas where you get a lot of things called liquefaction, or things change the area that you built your house on. In Michigan, if we were to have earthquakes, we have a lot of thick alluvium, so we would have really destructive earthquakes if they were to hit in Michigan. Luckily they don't. But the relationship between the intensity and the geology of, this is the 1906 San Francisco earthquake, is a known fact. And by looking at the soil type and the bedrock and everything else, they look at the amount of destruction based upon these different, either, in this case it wasn't a Richter scale evaluation, they were just looking at the relative destructive force of the earthquake and how much, how many houses fell down or burned up or whatever. And most of the destruction was in areas where, well, here we have alluvium that's not very thick. Here we probably got liquefaction in the San Francisco Bay. And anyway, factors that determine the earthquake's intensity include like the distance from the epicenter, the focal depth, the population density, because we're just talking about destruction, we're not really looking at the energy of the earthquake, the geology of the area, if it has, mud or water nearby, or if it's bedrock, and then the type of building construction. In the United States, we use some pretty good building codes now that we know that earthquakes hit pretty regularly. And then the duration. That's the biggest one that we think when we think of the destruction, how bad an earthquake is the duration of how long the ground actually shakes, because there's some synchronicity between certain waves that will cause much more destruction. If a building waves long enough, eventually it will fail. So how do we determine the amount of energy is released? Well, we look at the waves themselves. So here we look at the waves themselves, where you have distance, first and second, primary waves, secondary waves. And this translates into a magnitude based upon these distances right here. If you look at the distances in kilometers, and this is in seconds, and this gives us the magnitude, so this would be a 5, and this is the amplitude. If you go over here, so here's the time, like the distance between the first and the second one, that's in 24 seconds, and we know that that falls on a scale here, and that translates into a point on the magnitude scale here. And then you got the amplitude, which is how high, how big the shaking would be in a sense, and it also translates to a specific point. So we measure the amplitude of the largest seismic wave on the seismogram, and then we look at the height of the largest amplitude is converted to a numeric magnitude scale. And this is a base 10 logarithmic scale, which means the difference between a 4 and a 5 is pretty big. That's a 10 times more, tenfold increase in the wave amplitude. So how big this wave is, it's 10 times bigger. which means there's 10 times the movement of the Earth. But what's even more interesting is that's a 30-fold increase in the energy that is released. So this is base 10 if you just look at the amount of movement of the Earth and the amount of the amplitude of the waves, but it actually translates into 30 times each scale. So this would be 30 times greater from a 4 to 5 for the amount of energy that is released. And like I said, it's determine what determines the amount of shaking is the type of material that's underneath buildings or whatever it is we're concerned about. If it's bedrock, bedrock doesn't move all that much. It does have an elasticity, but it's not very much, and it takes some time to move it. Whereas you get well-consolidated sediments, they move pretty, not well, but they'll move a little more than the bedrock, and then of course poorly consolidated sediments, which means there's a lot of space and different sizes in there, will cause some more shaking. And then bay mud is water saturated, which causes liquefaction, and that's a little different. Actually, liquefaction may actually happen in the poorly consolidated sediment as well. But it also depends on how long it shakes and how vigorous it is, and if it's loose or wet material that's around it versus solid rock, which means it gives you torsional forces, which is a movement that is not all one motion. It's a bunch of different motions because the sediment is all different sizes and shapes, which means it causes a bunch of shearing, or the torsional forces cause shearing of buildings and things like that, which produces something that looks like that, which is a liquefaction when you're near any source of water and buildings sink into the ground. So if there's an earthquake in, let's say, Salt Lake City, the people in Salt Lake City, the geologists expect it to be really bad because the buildings are on the old Bonneville Lake bed, and if there's a really big earthquake, that water table will move up, and the buildings that were originally on pretty solid land, it'll turn into mud, and the buildings will sink into the ground and fall over, which is very destructive. And then of course we have issues related to fire. We have natural gas and water lines, and when you get an earthquake, we have pilot lights as well, and some don't rupture, and suddenly you have buildings catching on fire all over the place because the gas line breaks, but the pilot light is still working, and you end up with explosions and fire. In the case of the earthquake in 1906 or 1909 or whatever, I can't remember when it was, the fire is a result of everyone having fireplaces and stoves in their houses that get shaken and they fall over and catch on fire. And then of course we have the tsunamis. These are killer waves, which are earthquakes that generate huge waves, and that's usually the movement of the accretionary wedge. So there's an accretionary wedge here due to the subduction of the Pacific underneath the Eurasian plate, and it pops out, which causes an upwelling of the ocean, which of course creates this wave that is kind of it's not really noticeable if you're out at sea because it's very long, but that energy that's in that long wave builds up on shore when it gets shallower and shallower, and you end up moving all that water onto the shore. And this is the one from 2011, which is the Japanese earthquake, and it was pretty dramatic. And there's the one in 2004 as well that happened in Sumatra. And then, of course, there are land failure or ground failure, which triggers landslides. And I had this real interesting experience when I was a kid. I went to an area like this where they had a landslide, and we were driving around the lake that was produced, and there were houses underneath the water. The water was really clear, and I could see curtains in the windows of these houses just sitting there. It didn't water didn't rush in. It filled up very slowly. There's nothing they could do because they couldn't release it in time. And this town, I don't remember what town it was in Utah, got filled up with water, and they basically didn't know what to do. They eventually drained it, but all of those houses and everything were basically gone. Well, not gone. They're just, you can't, it's like flooding a car. It doesn't work after you flood it. You got to rebuild it. So, what you see here, this is a normal fault here, which means the footwall. Well, let me think about that. The hanging wall is moving down with respect to the footwall. Yes, this is a normal fault. So you end up with a fault scarp. You can see it. You also see how much the land moved here during the earthquake, which here, this is, I don't know, probably 5 feet, right? And that's pretty big earthquake. If you suddenly move the land 5 feet, that's a big wave. And most of the time when we talk about earthquakes, like I said, it's stuff falling on people's heads. and buildings falling down and rock slides. That's what kills most people. And then when we look at the waves, that's still the same kind of thing. It's building debris and everything else that kills people. It's not the water per se, it's what's in the water. And then, of course, we go to the San Andreas Fault, which we're all familiar with. It's the famous fault in California due to a strike-slip fault, due to the contact between the North American and the Pacific Plate. And they slide across each other and produce a whole bunch of earthquakes. And what happens after the ground failure is buildings collapse. Of course, you call in the National Guard because people start looting stuff. And I obviously don't, I would never want to be on a freeway in LA or anywhere if there was a big earthquake, because they do fail. I mean, we try to do, a pretty good job, but they do fail and people do die when they're sitting on these overpasses. So how do we predict earthquakes? Well, we know that they're going to happen along the Pacific Rim, and they're also going to happen in the Eurasian, Indian, Mediterranean zones because of where those continents are interacting. And so we already know that they're happening in these areas, and so we basically make seismic risk maps, which is what you see here. These are acceleration of areas of the land over meters per second squared, which is how bad would earthquakes happen based upon what we know about subduction zones in these areas. If you notice, Michigan is it's up here. We do have some areas, and that's due to the New Madrid fault, and there's, I don't know what fault's up in Canada, but there's something going up in Canada up there. But we're in a pretty safe zone because we're on the shield. We're on the Canadian shield, or pretty close to it here. So we don't have to worry about much. But what we do is we look at seismic gaps. We try to determine where earthquakes have occurred in the past, how often they have occurred, and gee, there's one that's missing. We haven't had an earthquake in so many years. And for the big faults, it's usually around 25,000 years that we start looking for another big earthquake. I mean, they have earthquakes all the time, but it's not those huge releases. So short-term and long-term changes within the Earth prior to an earthquake usually assist in our prediction. So we have things like, locked portions of fault where the pressure is building. There'll be changes in the ozone. There'll be changes in the water table. There's all sorts of interesting things that happen when you look at earthquakes. And these are all predictors of either rock that's going to be released, because that energy that builds up in the rock as the rock bends changes the magnetic field of the Earth. So it's a pretty big piece of rock. And we monitor these faults and say, well, it looks like we are going to have an earthquake. The problem is we don't know when, because we're dealing with such a large time frame. If you're talking 25,000 years or 25 million years, depending on what kind of fault you're talking about, it's very hard to narrow in on a day or a second. I mean, it's impossible. Here's what I find interesting too in this picture. Fracking causes earthquakes. We have observations and measurements of this happening. It happened in, I don't know if this is, 1960s, when they were pumping wastewater into the ground in Denver or somewhere in Colorado Springs, and they would pump the water in. That's what you see here. They pump the water in, and they start reading earthquakes. This is the amount of water that they pump in, and then the earthquakes. They said, we'll just pump it into the ground. We don't have to worry about it. And what happens is they pump it in because the pressure builds up. They start fracturing old faults and other things. And then when they stop pumping the water, it goes back to background level. There's like 1 or 2 earthquakes. This is over 1 year. And then they start pumping water again. The earthquakes go up again. So subsurface injection of liquid waste does generate small earthquakes. This was Denver. That's what it says in the book. And we know that we can release small amounts of energy stored in rocks by pumping. This has been proposed as releasing stress in rocks so we don't have the major earthquakes. The problem is because it's a logarithmic scale. It would take 10 Richter scale 7 earthquakes to release the earthquake so that you wouldn't have an earthquake that was at 8. So of course, if we had the big ones like the 9s that we have that are really destructive, it would take 100 7s in order to release that stress, which means obviously you're going to decimate everything if you have 7, or if you have 107 magnitude quakes. So it doesn't really release it's not a good idea. So the earthquakes basically give us an idea of there's some activity going on in the planet, and we know. So in this is a I don't know if you guys ever had the everlasting gobstoppers, you know, the ones that give you cavities and they're basically sugar, but they look like this. And you usually throw them out before you finish them because they're the size of a golf ball, and then you suck on them forever, and pretty soon you have, you know, canker sores in your mouth, but they're still about the same size. So, but they're different flavors, and they have this concentric layered effect, and it always looked like a planet to me. So you have the crust. Of course, we have the oceanic crust that's less thick than the continental crust, and that's due to density issues. And then you have the upper mantle, which then transforms into the asthenosphere, which is very plastic as temperature goes up, and then the lower mantle, which is very rigid. So this is rigid above, you have the asthenosphere, there's some movement there, and then you have the lower mantle, which is rigid. And then if you go down even further, you have the outer core, which is liquid, which gives us the magnetic field. And then, because this is all ions that are moving around, very large amount, like think of it as iron and other materials that are interacting, creating a magnetic field. And then of course the inner core, which is solid and warm, very hot actually. And it's earthquakes that actually help us identify what levels and what what the planet looks like. And so if you have an earthquake and you have certain waves moving through it, some waves, which is the primary waves, will move through liquid. The secondary waves will not move through liquid. We'll see what that looks like. So in this case, we know that as the waves move through and they hit a liquid, they actually get refracted, which means they travel at a different rate, and then they hit the solid part of the mantle again and they speed up. And we know this works for light as well. If you see light entering water, as it enters water, it gets refracted and changes the angle at which it travels through the water. And so we study the bending and the refraction and the reflection of the P and the S waves to understand what the interior of the Earth looks like. And so we have these changes. So here we have an S wave, and it reaches about a certain depth and just disappears. It stops. In this case, it's like, 2,900 approximately, which means that the core turns from solid to liquid about that point. Now, the velocity of the P wave, because it's a compressionary wave, not a side-to-side or that circular motion type of wave, and I'll explain what I mean by that in a second, but as these waves move through, the P wave slows down, then it hits the inner core again and speeds up a little bit, and then you'll get the same type of pattern on the other side once it goes through the inner core and then comes out the other side. If it actually does hit the inner core, excuse me. Now, this is sort of like trying to cause a wave in water. So if you grab a ruler and you move it back and forth, that ruler will move back and forth, and then let's say you stick it in the water, the ruler's still attached to your hand. In a sense, it's compressionary wave, it's moving back and forth. Now try to grab the water, you can create a movement in the water, but the minute that moving back and forth of solid object like the ruler, the minute you move into water and you release the ruler is not going to move anymore, right? Because it's not, when you think about the circular motion, it's like punching water in a sense, as opposed to punching a wall, which you don't want to do because it's solid. But the idea is that a liquid doesn't move side to side, but it can be compressed. That was the idea when I was talking about the water. You see the waves on the surface, these kind of waves, but there is no surface on the inside of the planet. And so these waves don't propagate well. The secondary waves don't propagate well if you enter a liquid. Now all of these layers that we're looking at, they're called discontinuities. Discontinuities for the secondary waves, discontinuities in the rate of propagation or the amount or how fast it moves through any of this material for the primary waves. This is what it looks like. So if you look at the primary waves, they move through, they get refracted, some get reflected, and they move at a different rate, and then they get reflected again, which means they get bent, and they appear on the other side. If you have the certain waves, they appear at a certain time. And so think of these all the time. This is going to appear first, Like if you have all these seismographs all over the place, the one that's going straight through, which is the shortest distance, is going to reach here, and then you're going to reach some other earthquake activity much later on these ones that are crossing because they travel at such a long distance as they move through. Like they go here, they bounce here, or they refract here, and then they refract over here. So these primary waves arrive much later than the one that moves directly through. And doing this, they know that there's a shadow zone of 103 to 143 degrees where there are no P waves, and that's due to the refraction. So we know that there's a sudden decrease in their velocity when they reach the core mantle boundary. That's the outer core. And we know that they are strongly diffracted or refracted in the liquid outer core. So few of them, or none of them actually, I would say few, some weird things happen in the Earth, but there's very few that we actually see between 103 and 143 degrees off of where that off that circle where that earthquake occurred. In this case, we call it the P wave shadow zone. And it's the same kind of graph here for the core when we look at what's going on in the core. The secondary waves, there's a shadow zone from 103 degrees to 103 degrees, and that's how we figure out that this is the point at which the liquid outer core, the depth, depending on the angle, so they just use trigonometry, and they say, based on trigonometry and the angle of this 103 degrees, we know that the liquid core is 2,900 kilometers underneath the Earth's surface. Then, as we get these discontinuities also occur very near the surface, so this little blip right here, this is called the MOHO, which is Mohorovicic. I can't say his name. He's a guy from the eastern part of, it's not Russia, or it might be Russian, but he's a very well-known geologist that said, hey, when I look at the way, the rate at which the speed of these waves move through the rock, there's a pause or a delay for some of the primary and secondary waves, and this is the zone between the asthenosphere and the upper mantle. And they call it the MOHO zone, which is what this slide shows you right here. So you have the density and composition of the core, we know that, and then we have the density and composition of the inner and the outer cores determined by the P and S waves, and then we actually look at the lithosphere and the asthenosphere based upon, like I said, the MOHO, and this is what it looks like. You have the epicenter of the earthquake, and if you don't actually enter the MOHO zone, which is that transition between, excuse me, excuse me, sorry, it's late at night, between the crust and the mantle, is known as the Mohorovicic discontinuity, or MOHO discontinuity, and it was discovered because of the refraction between, as you move down through from the crust into the mantle, you end up refracting the wave as it speeds up or slows down in this case, and then it ends up appearing at a different time. So you have two P waves or two S waves depending on what you're looking at, and one will arrive later than the other one, even though they're the same wave originating in the same earthquake. And this is what it looks like. You have depth, velocity as it moves. You go, okay, well, it's moving, hits a certain point, variation due to partial melting, low velocity zone, slows it down, and then you have a transition zone, another transition zone. So we have, this is, think of the asthenosphere. That's what I was trying to remember. Most of the material, we think, in the mantle, lower mantle asthenosphere is something called peridotite, and it represents basically most of the rock in the mantle. It's a very mafic, deep, dark colored mafic rock, and we think because of the physical properties and density, they account for the change in the seismic wave velocities in the mantle versus the crust. We use experiments to determine this. So we actually have run experiments to see how fast waves move through peridotite based upon the physics, and we say, oh yeah, this is what it must be made of, because we actually don't know. No one's drilled down into the mantle. I mean, it's, you know, it's several 100 kilometers underneath the crust. Based upon what we know about the movement of these waves and also mining, we know that the Earth is warm, and its temperature increases due to radioactive decay in the mantle, particularly uranium, thorium, and potassium-40. And if we look at the upper crust where people are mining, so this would be within the first several kilometers of the Earth, we see that it's about 25 degrees Celsius per kilometer, which is pretty warm. It's like, upwards of 70 degrees per kilometer you go down. And there's some areas where they go down to, if you go into a mine, it's actually like 110 degrees even though you're underground because of this heat. And then once you get down further in the mantle and the core, it's only about 1 degree Celsius per kilometer because you reach a certain point and you don't heat it up all that much more. And actually the Earth is getting cooler because of the radioactive decay is causing these the uranium and the thorium in there to turn into lead, basically. And we believe the center or the inner core of the Earth, if you follow this down, it's estimated to be about 6,500 degrees Celsius, which is about the temperature of the surface of the sun. It's pretty warm. And we've already gone over this. This is why I don't really have pictures, because I just want to mention it. But we have the continental crust is mostly granitic and low in density. It has an average density of 2.7 grams per centimeters cubed, which basically, P waves travel through that at 6.75 kilometers a second, which is pretty fast. Also, keep that in mind, 2.7 grams per centimeter cubed will be a number that you want to remember for when you do the labs, when you look at the density of rocks. And, of course, the continental crust averages about 35 kilometers thick, and it's thicker along the shields where we are, and then on the mountain ranges, so the earthquakes aren't as dramatic. And then we have the oceanic crust, which is mostly gabbro, which is a little more dense, which means earthquakes don't propagate as well. They don't propagate as well in the oceanic crust. And it has an average density of 3 grams per cubic centimeter, which means the velocity is 7 kilometers per second. Oh, let me think about that. Actually, yeah, let me reverse what I just said. Because the oceanic crust is more dense, it's actually going to propagate the waves better, not worse. That's what I meant to say. I've reversed that. And it ranges from about 5 to 10 kilometers thick, being thickest around, of course, the spreading ridges. Ridge push, lab pole, remember? So conclusions. We have the elastic rebound theory explains how energy is released during an earthquake. We have seismic waves cause most of the damage and shaking people feel during an earthquake, plus the landslides and everything afterwards, falling of buildings and other issues, the hazards that we have from an earthquake. Locating an earthquake requires triangulation of the seismographs. An earthquake, and we use the P and S, so the primary and secondary waves to do that. And the earthquake's intensity is expressed with a modified Mercalli intensity scale, which means how much destruction. I didn't really talk about that much, but basically how much destruction occurs. And then the magnitude is measured by the Richter scale or the seismic moment magnitude scale, which is the amount of energy that was in the earthquake. And understanding the Earth's interior should help us to predict earthquakes. And then the earthquakes are produced by heat, pressure, and structure of the Earth's crust. And then it should help us predict earthquakes as well. Thank you.